And good morning, everybody. Here are your notes for section 3.3, and we're going to be talking about increasing and decreasing behavior of a function, and we're going to be using the first derivative, f prime, to do a test on it and see where the function is going up and where the function is going down. And before we get too far into the official notes, let's just talk about the big idea. So let's say we had some function, let's call it f of x. So we have some function f of x, and let's say it's going on an interval from a to b, and it's going up and it's going down. So if we kind of look at just some portions of this curve, notice this part of the curve, it's obviously going up. So if you think about what the slope values are on that section of the curve, the slope values would be positive slopes. So all your tangent lines would have some sort of positive slope. So your slopes are going to be changing, so the value of your first derivative will be changing, but all the first derivative values are going to be positive. So f prime, the first derivative, on that particular section of the graph is going to be some sort of positive number. So it could be a slope of maybe positive 2, then positive 1, then positive half, then positive a fourth. All your slopes are going to be some sort of positive number. When you get to the top of the curve, your critical value, we studied critical numbers, your critical value, your first derivative is going to be 0. So that's going to be a critical number. And if you look at a second part of the curve, so after that critical point, if we start to look at the slopes on this part of the curve, notice they're all going to be negative slopes, so all your tangent lines are going to be negative. So f prime will be negative in value. So whatever value you're getting for an output on f prime, all your outputs on f prime are going to be negative outputs. So we're going to be investigating where f prime has positive outputs or negative outputs. Because if you have positive outputs on f prime, then that means your slopes on f must have been positive slopes. And if you have negative outputs on f prime, then your slopes on f must have been negative, so the function was going down. And then you'll have another critical point here where f prime is 0. So that's your critical value. We studied a packet or two ago how to find those critical values by setting your derivative equal to 0 or undefined if it's a sharp turn or something. So where your first derivative is 0 or undefined, that's going to be your critical points. And then on the other side of this second critical point, so there's our second critical point, if we look back again at the slopes, it's going to have positive tangent lines. So all your tangent lines are going to be positive. So f prime would be positive. So when the function is going up, f prime is going to be positive. And when your function is going down, the value of the first derivative is going to be negative. And when your function is potentially changing direction, that's going to be a critical point. So that's where f prime is going to be 0. So f prime equals 0. Those are critical points, or undefined. And you have a potential change in direction. It's not always going to change direction. For example, you could have a graph that had a slope of 0, and then whatever direction it was going, it continued on. So for example, maybe if you had, make some room here. Maybe you had a function that was kind of going up. So it was going up. It had a slope of 0 for a second, and then it kept going up. So its first derivative is going to be 0 right here. But it doesn't have a change in behavior. It was increasing, went flat for a second, and kept increasing. So your slopes would have been positive slopes. So f prime would have been positive, f prime would have been 0 right here, so f prime would have been 0. And then after f prime was 0, f prime would have been positive again. So when f prime is 0, you have a critical value, but you don't always have a change in direction. You're going to have to test for that, and that's where the idea of the first derivative test comes in, because we're going to use the first derivative and do an interval test to see where it has a sign change, where it changes from positive to negative or negative to positive. That's going to be where we have a change in behavior as far as increasing or decreasing goes. So let's just go ahead and read through your official notes. So here's the notes for section 3.3. So increasing behavior on f, function f is the original function. We would consider it increasing on some open interval from a to b if, for all the c values in that interval, your first derivative is greater than 0. So basically f prime would have to be positive. So if f prime is positive, then f is increasing, is what that is saying. The second one, your function is decreasing, f is decreasing on an interval from a to b. If, for all c values in that interval, your first derivative is negative. So if f prime is negative, then f, the original function, has to be decreasing because it's saying that all the slopes are negative. So remember, this value right here coming out of f prime is talking about the slope values. So you're saying you have negative slopes on f. And the third note, a function is considered monotonic if it doesn't change its increasing or decreasing behavior. So if something is always going up or if something is always going down, then we would consider that monotonic. So a linear function is a good example of a monotonic function. So that is always going up, or a linear function could be always going down, would be one example. Another example could be exponential growth or exponential decay. So an exponential growth function, exponential growth curve is always going up, or an exponential function is always going down if it's decay. So that would be an example of monotonic. So your first derivative is not going to change value. On this one, f prime would always be positive because the slopes on f are always positive slopes. And in this example, f prime would always be negative because your slopes are always negative slopes. They approach slopes of 0, they'll never get to a slope of 0, but there'll always be some sort of negative slope value. To decide where f prime changes its sign value, we're going to set up what we call an interval test. So we're going to be testing on some interval from a to b. And we're going to be looking at the output values on the first derivative. So job 1, we'll have to find the critical values. So remember, your critical values are where f prime is 0 or undefined. So we'll find our critical points. And then we'll test numbers, test input values between those critical numbers, and we will see what the output is on f prime. And those output values will be telling us what the slopes are on f. So for example, if we just look at this first one, we tested a number between a and the first critical number, and it looks like the output was a positive output. So if the output was a positive output, then that means you have positive slopes on f, which means f must be increasing. And here, f prime on the second one, between these two critical numbers, C1 and C2, f prime was a negative output, so that means you have negative slopes on f. So for this one, your function would have been decreasing. So in this particular interval test, your function was going up, and then it changed direction and it started going down, and then it changed direction and started going up, and then it changed direction and started going down. So your function was going up, then down, then up, then down. And this next part of the notes, this is basically telling you how you can do a first derivative test on your graphing calculator with a graph. This is kind of old as far as it doesn't really match up with our new operating system on our calculators. So this right here is kind of old syntax for a TI-84 graphing calculator. So at the end of this lesson, we will do one on our graphing calculator and show you how we're going to put it into our graphing calculator. So for now, we can kind of skip over this, and we'll do it at the end. And here's our first example. So they want us to find where the function is increasing or decreasing. So we're going to look at the values on the first derivative. So job one will be to find a first derivative. So we want to find f prime. And that's going to be 3x squared. And then bring your 2 down. So your 2's are going to cancel. So minus 3x. And we need the critical values, so we're going to set our first derivative equal to 0. We'll factor out a 3x. And if you distribute 3x back in, you get 3x squared and 3x, so that looks okay. And then set those equal to 0, so if x is 0, your final output for your function is 0 if x is 1. That's another solution where f prime was 0. So these are the critical numbers. So these are the critical numbers. So if the function f is going to change direction, it's going to take place at these particular critical numbers. So what we want to do is set up an interval test. They didn't give us a particular interval from a to b, so we'll assume we're testing the entire function. So its domain would be from negative infinity to infinity. And we have a critical number at 0. And we have another place in the graph, a critical number at 1, where it could potentially change direction. And then we want to look at the values on f prime, and that's going to tell us what's happening on the original function f. So we know here at our critical numbers f prime is 0, since we just solved for that. So we want to know what's happening with f prime on this interval from negative infinity until we get to that first critical number. So you want to pick a number anywhere between 0 and negative infinity. So just choose a number somewhere between 0 and negative infinity. Doesn't matter which number. Pick an easy number. So let's test where x is negative 1. So if we put negative 1 back into f prime, so if we went in and tried to find the value for f prime at negative 1, and we plug that value back into f prime. So if we do 3, negative 1 is going to go in, and then negative 1 minus 1, so that's going to get me negative 3 times negative 1, that's negative 2. So that's going to be positive 6. So f prime is positive 6. So that tells us that f prime is going to be positive for any number that we test between negative infinity and 0. To shorten things up, you don't need to necessarily find the actual magnitude or size of this value. You just need to know whether it's positive or negative. So another way to do it is if you looked at your factored form. If I put a negative 1 into this particular factor, then that's going to work out to be a negative number of some sort. And if I put a negative 1 into this one, then that's going to be a negative number. And a negative times a negative is always going to work out to be positive. So you don't need to find the actual value, you just need to determine whether it's positive or negative on that interval for f prime. So if f prime is positive, then that means function f must be increasing because the slopes are all going to be positive on that particular interval. At our first critical value, we know the slopes are going to be 0 because we solved for that. F prime is 0. So now we need to test another number, something between 0 and 1. So maybe think about a positive half. So if we put a positive half into f prime, so we'll go put a positive half into f prime. And again, if you just think about what's going to happen to the factors when you're looking at f prime, so if I put a positive half in this first factor, if I put a positive half into that, a positive half times 3, that's going to leave you with a positive number. And then if you put a half into this second factor, put a half in, you're going to get 1 half minus 1, that's going to leave you with a negative number. So it's going to be a negative number. And they're multiplying these two values together, so it's going to be a positive number times a negative number, so overall result is going to be a negative value. So f prime is negative at that 1 half, so that means function f must be decreasing. And then we need to test another number, something between 1 to infinity. So maybe like the number 2. And if we put a 2 into the original f prime, so we need to know what f prime of 2 works out to be, whether it's positive or negative. So on the first factor, 3x, if you put a 2 in there, that's going to get you a positive number. Getting a little messy, but let's keep track of this. So that's going to get us a positive number on the first factor. And if we put a 2 into the second factor, that's going to get us a positive number. And we should know that a positive number multiplied by a positive number will always be a positive number. So f prime at 2 is going to be positive, which means f must be increasing. So that's going to be your first derivative test to show where f is increasing and where f is decreasing. And then one more final step is we want to write our final answers in interval notation. That's how you're going to see them in most answer keys. So let's go ahead and put this in A, B interval notation. And let's just make a little bit of room so we can do that. So let's erase some of this work. So we know it's going to be increasing. So for a final answer, f is going to be increasing on the interval from negative infinity to 0 and on the interval from 1 to infinity. So those were the two intervals where f was said to be increasing. And then it was decreasing from 0 to 1. So that's going to be your final answer. So that's our final answer written in interval notation. You can make a graph of it and kind of see if you are correct. So this is a graph here of the function. Does it match up with what we determined from the first derivative test? It looks like it is increasing on this interval until it gets to that first critical value where x is 0, and then it is decreasing from 0 until it gets to its next critical value, which was 1, and then after an x value of 1 it was increasing again. So you can take a look at a graph and kind of see if your answer looks reasonable. Here's an example of justifying that a function is monotonic. So a function is monotonic if it's always increasing or decreasing. So again, we'll use a first derivative test. So let's find f prime. So f prime will be 3x squared. Then we want to find the critical numbers, set it equal to 0. And solve. X would have to be 0, so that's a critical value. And then we will do a first derivative test. We will test it on the entire domain from negative infinity to infinity. We have a critical number at 0. And we will see what kind of sign values we have on f prime. So we'll test a number between negative infinity and 0 into f prime. So maybe we can test a negative 1. So if I put negative 1 back into f prime, you're going to get negative 1 squared, which is positive 1, so you get a positive, and then a positive times a positive 3 is still positive, so f prime will be a positive number, which means f is increasing. And then we'll test another number between 0 and infinity, like maybe positive 1. So if we put a positive 1 into f prime, we're going to get 1 squared, which is 1 times 3, so positive 3, so it's going to be positive again. So again, f prime was positive on this interval, so that means f must have been increasing. So it was increasing and increasing, so that would be considered monotonic because it is always increasing. It does not change direction and go from increasing to decreasing or decreasing to increasing. And again, you can kind of check this by looking at a graph. It was increasing, had a derivative of 0 for a moment, right here where x was 0, you would have a slope of 0. So that's why f prime was 0. And then after f prime was 0, after it had a slope of 0, it continued increasing again. So it was increasing, slope of 0, and then increasing, so that would be monotonic. This one is an example of how to do a first derivative test using just your graphing calculator, so just looking at a graph of the first derivative. If you think about the two pieces of information that you need to do a first derivative test, you pretty much need two pieces of information. You need to know where f prime is 0, or in some cases undefined. That's going to be your critical points. And you need to know whether f prime is positive or whether it is a negative output. So whether it's positive or it's not writing well. So where it's positive or a negative output. And you can get all that information just by looking at a graph of f prime. So to get a graph of f prime, we're first going to put in our original equation into the y equals menu. So we're going to put in the original function into y1, and then in y2 we will go ahead and tell the calculator to graph the derivative of this. So I don't know if you can see that. So it's my first time doing this. So putting the equation into your y1. So you want to put the original function into y1. So put your original function into y1. And then to get a graph of the first derivative, we're basically going to ask the calculator to take the derivative of y1. So in y2, you want to ask it for the derivative, so you can go to alpha f2 and go to that menu and find your derivative and click on that, and then you can go to alpha f4 and find your y1. So this is going to say take the derivative with respect to x. You'll have to type the x in right here. Take the derivative with respect to x of function y1, and x is going to be equal to all possible x values, so you're going to need to type an x in right here. And if you just want to look at a graph of the derivative, if you go put your cursor on this equal sign for y1, hit enter, and it will debold it, it will disengage it. So if you have just this one bold or engaged, when you make your graph, it will be just a graph of the first derivative f prime. Once you have a graph of just f prime set up in your y equals menu, then you can go ahead and choose an appropriate viewing window. So this is just a standard 10 in every direction, so zoom 6. So what you're seeing here is a graph of f prime. So this is a graph of f prime. And remember, what we need to basically know is where f prime is 0 and where f prime is giving you either positive outputs or negative outputs. So where f prime is 0 will be the zeros of f prime, so where it crosses the x-axis. So you're going to look for the 0 here, and f prime is going to be 0 here. And you can use the 0 feature of your graphing calculator to find that, or if you have an educated guess, you can trace it. Type in the number that you think it has a 0 at, do trace, type in that number, and see if you get an output of 0. So using the 0 feature of your graphing calculator, or just tracing it and typing in a number to see if you get an output of 0, we should find that we have a 0 on f prime at -2. So the output on f prime is 0, so that's going to be a critical number. So at x equals -2, we will have a critical number. And then we have another 0. This is pretty much 1. If we did this by hand and solved by hand, you're going to get x equals 1. The calculator, that's the best the calculator can come up with. So at x equals 1, f prime is going to be 0 there. So those are our critical values of function f. And then we can go ahead and do our number line test now that we know what the critical points are. And now that we know what the critical points are, we can go ahead and set up our number line test. So we know we're going to be looking at a critical value of -1 and a critical value of 1. And we'll test this on the whole domain of f. And we're looking for f prime and f. So the next question is, well, how do you test a value in between -infinity and -2 to see what the output is on f prime without doing any handwork? If you're just solely using the graph of f prime, remember we're looking for the output on f prime, which are basically the y values. So we're looking for the outputs or the y values on f prime, and we're looking to see if those y values are positive or negative. So if we look from -infinity to -2 on the graph, so that would be -2 is here, so anything that is this way on the graph, if you look at your y values, so these would be your y values. If you look at your y values on the function, again, we're not looking at the slope on f prime, we're just looking at the y values. So the y values on this part of the function, those are all positive y values, so we're going to say that is going to be positive. And then from -2 to 1, again, we want to look at the y values. So from -2 to 1, we're just looking from here to here, and notice all the y values, all the output values on the graph are below the x-axis. So if all the y values are below the x-axis, then they must be negative y values. And then if you look at the x values to the right of 1, notice all your y values are above the x-axis, so those are all going to be positive y values. So that's going to be positive. So that will tell us that the original function is increasing, then it's decreasing, and then it is increasing. And that's without doing any of the handwork, without doing any algebra. You can just go through and look at a graph of f prime and do a first derivative test and decide where f was increasing, decreasing, or increasing. And then again, to put that final answer into interval notation, we can say it was increasing on the interval from negative infinity to negative 2, and also on the interval from 1 to infinity, and it was decreasing on the interval from negative 2 to 1. And remember, this is a graph of f prime. Don't confuse it with us talking about what is happening on f. We're not looking at a graph or a picture of function f right now. We're looking at a graph of its derivative, f prime. So if you want to see if this checks out, if this looks reasonable, go back to your y equals menu. So you can go back to your y equals, disengage the y2, so turn y2 off, but go turn y1 on, make a graph of y1 on your viewing window and see if it matches up with your increasing and decreasing behavior that you found from the first derivative test. And that should finish up all the examples for this particular packet, section 3.3 on increasing, decreasing behavior in the first derivative test.